Hello, my name is Jacob Eriksson. I'm a professor in the UIC Department of Computer Science. In this video, I will try to convince you that you should take my class CS494 Safe and Efficient Systems Programming with Rust in the spring of 2021. If you haven't heard of Rust before, it's a new systems programming language. Its main claim to fame is that it eliminates most memory safety and concurrency bugs. This means no more buffer overflows, no race conditions, no null pointer exceptions, no seg faults. All of these are due to bugs that are permitted by, say, a C program, but can't really be expressed in Rust. It's also a modern language with many attractive high-level features, while offering low-level control of resources, which is what makes it a systems programming language and makes it a viable replacement or complement to C or C++. Generally speaking, Rust programs are very fast, but more importantly, they're less likely to crash at runtime than programs written in C or C++, or even in Python or Java. To give you a little flavor of what Rust is all about, I'm going to go through some small program examples and discuss some Rust features along the way. So here's a very simple main program. It assigns 0 here to a variable I. We increment I by 1, and then we print out the value of I to the console. Now, of course, I could have been a little more specific. I could have told the compiler that I want this I to be a 64-bit unsigned integer by specifying the type. But in this case, I didn't, and the compiler then uses a default value for an integer in this case. In general, the compiler is very competent at type inference. So in this case, it uses a default type here for the 0, but then it infers that I should have the same type as 0. One of the high-level features of Rust that makes it very attractive. Okay, but if we try to compile this, let's use the normal version without the type annotations. We try to compile this, we immediately get an error. This is something that happens a lot in Rust. We get lots of compilation errors. The compiler is very strict with us, and we need to learn how to program safely, or we won't be able to program at all. In this case, the problem is that variables by default are immutable. You can assign to them once, but then that's it. So here the compiler says, okay, we have our first assignment to I over here, set it to 0, but then you're trying to assign to it again, and that's not okay. Fortunately, it provides a little bit of help. We might want to make our binding variable here mutable. Let's make that small change. So now we have a mutable binding I. Alternatively, we could use a new variable. In this case, a new variable also called I, and we could assign that to the value of the previous I plus 1. So here the new variable sort of overwrites in terms of the name. Later on in the program, we will be using this variable I to refer to it with an I. Okay, but for now, let's stick with the mutable version of the variable, and we'll see this case a little bit later. Right, so here's the mutable version. Mutable simply means it can be modified. If we run this one, you'll see the output will just be I is 1. Right, let's move on a little bit. Here I'm taking reference of I. You can think of the reference as simply a pointer to I from a C perspective. For now, I removed the I plus 1. We're not changing I anymore. And we're printing out the value of I and I ref here. Here's another interesting feature of Rust. I have a reference to I, and I can treat that under some circumstances as the variable itself. I don't need to dereference this. It automatically does that. Okay, if we try to compile this, however, we get some complaint. In this case, it's not an error. Compiler is simply saying, this variable I here that you made mutable, that's unnecessary, and you're inviting bugs by doing so. It'd be better to not have the variable mutable so that you don't accidentally mutate it later when you perhaps meant to mutate a different variable. Okay, so we could, of course, remove that, but instead let's remove this comment so we start mutating our variable. Actually, if we just run it this way, it'll print 0 and 0. Okay, so now we modify our code here, remove this comment. So now what would happen? Now we're getting into some interesting and slightly exotic Rust territory already. So we're trying to mutate this variable I, for which we already have a reference as well. Now, Rust doesn't really allow having multiple references to the same variable unless they're all read-only. In this case, we have one that's mutable, and then we have a immutable reference over here. So let's take a look at what the compiler says about this. So it doesn't want us, it says cannot assign to I because it's borrowed. It doesn't want us to modify the variable I anymore because someone else, in this case, this variable here, has a reference to the variable. So having multiple references invites concurrency errors, even if it's not from two different threads. You can have problems with function calls, or even in large functions, you might accidentally get your variables into an inconsistent state if you have multiple names for the same value, let's say. So Rust wants you to avoid that. Okay, so we can't do this. Actually, there's no way to really run this program. There's no real fixing this one. Rust doesn't allow it. But what about if we instead make a new variable, like in our previous example? So here we make a new variable I. That is the value of the previous variable I plus 1. Now we're not mutating the previous I here, and the iref is still referring to the old variable I. So this is legal Rust. Now we have a new copy, a second variable. Alright, so if we execute this one, we get that I, the variable here, is 1, but iref is still referring to the old variable I, which has still the value 0. To give you a little bit more detail here, this reference is a read-only reference. What if we make it a mutable reference? Which means the user of iref here, the owner of iref, has the ability to change the value of I, of this previous variable I, that is. In this case, this usage here is no longer allowed. We're trying to access the old value of I while there is a second mutable reference to that I. In principle, that I could change while we're accessing it, at least if this was a multi-threaded program. And in general, it's not really good from an aliasing perspective. Again, potentially creating confusion in larger programs. So here, compiler again complains, saying we are no longer allowed to use this I because it was mutably borrowed. That's the term for taking references previously. And this reference here is still live because we're using it down here. Right. So Rust takes very good care of making sure we cannot have memory safety or concurrency errors. As a result, we do get to fight the compiler quite a bit. This is of course good and bad. It can be frustrating at compile time, but it's wonderful at runtime. And you get used to it after a little while. So that's all I've got for this little example of the challenges and the benefits of Rust. I wanted to show you a couple other little things. Here's a simple function that computes the sum between 1 and the passed in parameter n. This is in imperative form, very similar to how you would express it in C. And just like a program written in C, the compiler would cleverly evaluate this at compile time, and at runtime it would be a simple formula rather than a for loop. In fact, Rust C is built on top, the compiler is called Rust C. It's built on top of LLVM, just like Clang. So many of the same optimizations apply to both languages. But you don't have to express things in imperative form in Rust. In that sense, it's closer to a high-level language. So the same program could be expressed this way. Here, we first generate an iterator between 1 and n, and then we apply the function sum, which is defined like this, and exists for any iterator with an element type that can be added. I won't go into the details here, but the main point is that this function generates the exact same assembly as the previous imperatively described function, a testament to the efficiency of Rust, as well as the expressive power of the language. Finally, if I have convinced you now that you should learn Rust, then why should you take a class in Rust? Or why do we offer a class in Rust? We don't offer classes in any other programming languages, really. Well, I firmly believe that learning Rust makes you a better programmer in any language. The Rust compiler is a tireless teacher of good memory and thread safety practices. Learning Rust is simply the best way of learning those very important concepts and skills. However, the learning curve can be quite intense, and Rust has a reputation for this. And I believe this is a challenge that will be better faced together. Other things we'll learn in this class is deeper knowledge about computer systems than what you picked up in CS494. And you may find that forward-thinking employers will appreciate an official credential in Rust. Right, that's all I've got, and I hope you decide to join us in the spring of 2021. Thank you.